Now, how do we solve this in practice? Well, uh, as I say before, we had the same problem that we don't know the distribution underlying the data, the random pairs x and y. So rather than using the true risk, we were in some sense forced, or we chose to use the empirical risk, and we can try to do the same thing again. So this is what we might call a naive approach. We replace simply the true risk with the empirical risk. Now, this empirical risk, as we know, is an estimator of the true risk. It's a random variable. So for each gamma, let's define the empirical risk of the empirical risk minimization solution. So what we're defining here is the empirical risk of the empirical risk solution f hat of gamma. So this itself comes from empirical risk minimization. So I'm going to call this z of gamma. So for a fixed gamma, I'm going to define z of gamma as the empirical risk of our ERM solution, and it's defined by this this arithmetic mean here, based on some random sample. Let me call that random sample D. So this is a set of random pairs xi, yi from I equals 1 up to n. Now f itself, f gamma of hat, is a random, not random variable, but actually random function. It's a random function for each gamma, because we obtain it by solving the empirical risk minimization solution, and this depends on our random sample, right? Because we've got an empirical risk here which depends on the random sample. And so in order to find this, we need to first have a data set. And as we go from one data set to another, this will change for a given gamma. Right? So this itself is random. It's a random function, not a random variable. It's not real valued, it's a function. We call it a random element. Now, what does model selection do in our naive approach? Well, it will select the value of gamma as gamma star by minimizing this z gamma, which is defined as the empirical risk of the ERM solution. So it solves this problem. It finds the value of gamma that minimizes this z gamma, which is defined as the empirical risk of the ERM solution. Now, this itself is going to be a random variable, right? Because everything in here is random. This z gamma is a random variable. The empirical risk is a random quantity which estimates the true risk, and we are estimating, so we have an estimator of the true risk, the empirical risk, of something which itself is random. It's a random function. So this gamma star is going to be a random variable. Now, the minimum risk that we will end up with once we choose our gamma star as the one that minimizes the empirical risk of the ERM solution is going to be simply z of gamma star. So that will be the minimum by definition over all gammas of z gamma, the way that I'm defining z gamma as so z of gamma is equal to the empirical risk of the ERM solution. Right? And we pick gamma star as the one that minimizes this over gamma. Let's put the gamma in there. The one that minimizes this over gamma. Right? So that's gamma star. And so by definition, the minimum of z gamma will be the one corresponding to gamma equals gamma star. So z gamma star. Now let's fix gamma to some value gamma 0. Then what do we have? Trivially, we have this. Z gamma star is less is going to be less than or equal to z at gamma 0, since this is the minimum one, right? So by definition, it must be less than or equal to z gamma 0 for any arbitrary gamma 0. Now let's take the expectation of both sides with respect to the distribution over our random sample, right? Now, here we can use something called, we don't need to bother about it too much, but the monotonicity of expectation. In order to do this, we're going to get the expected value of this is less than or equal to the expected value of this. Now, this is true for any gamma equals gamma 0. This is true for any gamma 0. So, since it's true for any gamma 0, then we end up with the expected value of z gamma star is less than or equal to the minimum of the expected value of z gamma. So here, let me be clear about what I'm writing here. Z gamma star is defined, by definition, is the minimum over gamma of z gamma. And that's why we have this equals this. And we also concluded that this expectation is less than or equal to the expected value of z gamma 0 for any gamma 0. For any. And therefore, if the expected value of z gamma star is less than or equal to this for any gamma 0, then it's true for the minimum over all gamma. The gamma that gives us the minimum of this over all gamma. So it's also true, so we can also write this is less than or equal to the minimum over gamma of the expected value of z gamma. Okay, so what is this telling us? Well, z gamma star is a random variable. And what is it equal to? It's equal to the minimum of z gamma over all gamma. And what we're asking here is what is the expected value of this minimum? In relation to what? Well, in relation to the expected values of the empirical risk of the different empirical risk minimizers for different gammas, or the empirical risk minimizers for different gammas. This expected value is a more reliable estimate because it averages over all random samples. So it's giving us a truer reflection of what would be the risk associated with a particular gamma, a particular hypothesis class. And then for each of these, we can take the minimum of this expected value, this average over all random samples. But we're not doing that. In our empirical risk model selection using empirical risk, what we are doing is we're taking the minimum from lots of different random estimates, these Z gammas. And this is telling us, so we're selecting the gamma based on this minimum or from lots of different random estimates. This inequality is telling us that this gamma that we choose, according to this minimum, is not going to be the same gamma that we would get if we minimized the expected values. In fact, which is a more realistic reflection of the risk across gamma, and therefore would give us a more robust value of gamma than this would. And this is systematically biased below this value. It's systematically less than this value. Typically, this will be a strict inequality. And so we have a type of bias in this procedure where we use this to select our best gamma, namely gamma star. And the gamma that we will get is not, this gamma star is not going to be the same as the gamma that we would get by doing this. if we could do it, which of course we can't, because we don't know the distribution over these random pairs. But what we do know is that this is underestimating this truer reflection of the minimum risk based on the empirical risk, or estimate of the risk based on the empirical risk. And this type of bias has a special name, and it occurs because essentially among different random estimates, we can often get one that's particularly low just by sheer chance. This is the fundamental reason for this type of bias, which we call selection bias. So by using our empirical risk, we have this type of bias, selection bias. But in addition to this, we have another type of bias, which we already know about. And that is in using the empirical risk to estimate the true risk. So our empirical risk estimate of our ERM solution is not an unbiased estimate of the true risk of the ERM solution, F hat. And this is because our empirical risk minimization solution, F gamma hat, is not a fixed function. We saw that the empirical risk is an unbiased estimate of the true risk if we have a fixed prediction rule or fixed function. In this case, we don't have that. So we can't apply this unbiasedness result that we got. And typically, what empirical risk will do is underestimate the true risk. It's again biased downwards. So the expected value of the empirical risk of our ERM solution is less than or equal to the expected value of the true risk of our ERM solution. Now, I'm not going to prove this here, but we will prove it later on when we take a deep dive into these the error decomposition. So why is this? Well, it's because when we perform the empirical risk minimization to get F hat gamma, the model will adapt to the noise in our dataset because we have only one dataset. If we then use the same dataset to measure the risk or to approximate the risk, we are basically cheating. It's like marking our own exam paper because the model has already adapted to the noise. So if we then measure the risk of that model using the same dataset, using empirical risk, in a sense, we are double counting it. We've already biased the result towards that particular model. So that model looks very favorable. But that's only because it's adapted to the noise in that particular dataset that we have. So let's try to quantify this type of bias. So this is another type of bias. Let's try to quantify it. And we can quantify it in the following way. So trivially, we can write that the expected value of Z gamma, where Z gamma is defined as this thing here. So Z gamma is defined as the empirical risk of the ERM solution for a fixed gamma. The expected value of this, or expected value of Z gamma, is the expected value of the true risk of the ERM solution minus the same thing, so that's minus this, plus this. So we can decompose this into this part and this part here. So this is trivially true because we've got this minus this, so it cancels, and then minus minus plus expected value of this, which is precisely that. Now this here we can call the optimism of the empirical risk. And this quantity is positive because the expected value of Z gamma is less than or equal to this thing here. So it must be equal to this minus some positive quantity, which we can call the optimism of our empirical risk estimate of the ERM solution. So in conclusion, by using the empirical risk to find gamma, we've got two sources of bias. We've got a selection bias and we have this optimism bias. And we can quantify this by this. The selection bias tells us that the expected value of the uh, the risk of the solution that we pick is going to be less than or equal to the minimum of the expected values of the risks, or the empirical risks over all gamma. Now we can combine these two into one. So from here, we have the expected value of Z gamma star is less than or equal to this minimum. And what is this? Well, we can decompose this expectation here as the expected value of the true risk minus this optimism. So we end up with the expected value of Z gamma star is less than or equal to the minimum over gamma of the expected true risk minus the expected value, sorry, not the minus the optimism in our empirical risk. So there are two components here in our bias. By using this procedure, using the minimum of Z gamma to find the best gamma value, gamma star, we face two biases, or we introduce two biases by doing this. One is a selection bias and the other one is this optimism bias. Now, this maybe is not entirely apparent at the moment, but no, actually it should be by now, that the empirical risk, if we use the empirical risk to find gamma, the optimal gamma, we are always going to get a biased estimate. And the reason for that is the selection bias. The other bias, the optimism bias, we can try to reduce. So this is what we focus on in using sampling methods, to try to get rid of, as far as we can, this training optimism.